All right, let's talk about the one thing, the single mechanism that turns a simple text predictor into a powerful AI agent that can actually interact with the world. This idea is the engine behind the entire agentic AI revolution.
Okay, let's start with a kind of controversial idea, but it's the absolute truth. By itself, a large language model is just a very, very fancy autocomplete. It has no hands, no way to check real-time facts, no way to act on anything. That is, until you give it a tool. Then it becomes an operator.
And this isn't just a cool tech trick. We're talking about a market that's projected to just explode to over $52 billion by 2030. And every single dollar of that growth is built on the concept we are breaking down today, the tool call. So how do we make that jump, from a machine that just predicts the next word to an agent that can actually do stuff? Well, we have to build a bridge. And that bridge is the tool call. It's the mechanism that lets a model ask for help to interact with the real world. And I really want to drive this point home. The tool call? It's the only reason agentic AI even exists. It is the absolute foundation for everything else that comes after. Okay, so how does this whole thing work under the hood? Well, it's not magic. It's really just a simple, reliable, four-step contract between the language model and your code. You can think of it as a very structured conversation. So here's how that conversation goes. Step 1. You send your message, but you also send a list of tools the model can use, described with JSON schemas. Step 2. The model looks at your request and decides if it needs a tool. If it does, it sends back a structured request. Now here's the absolute key part. Step 3. You, in your own code, execute the tool. The model never runs anything. Finally, step 4, you pass the result back to the model, and it uses that new info to give you a final synthesized answer. So, how does it even know when to call a tool instead of just making something up? Well, it's been trained for it. Through reinforcement learning, models get rewarded for using tools correctly and penalized for hallucinating an answer. So, the best way to think about this is really simple. A tool call is just a JSON contract. The model acts like a smart router. It proposes an action. Your code is the executor. It's the one that actually does the work. This separation is everything when it comes to safety and control.
All right, now let's get to the part that can literally supercharge your application overnight, seriously. Most developers are leaving this massive speed boost on the table because they're not using the feature that's already built right into the modern models.
Okay, so look at this pretty common scenario. An agent needs to grab 3 things: user data, their invoices, and their account status. Sequentially, you do one, wait, do the next, wait, you add it all up, and you're at 1.8 seconds. But what if the model could ask for all 3 at the same time? And bam! This chart just says it all. By running these calls in parallel, your total time isn't the sum of everything. It's just the time of the single longest call. In this case, that's a 55% cut in latency. That's a massive difference. Think about it. If you're running 10,000 of these a day, you're literally saving over 11 hours of cumulative waiting time. That is a huge deal for user experience. So how is this actually possible? Well, frontier models like GPT-4o and Claude 3.5 can return a whole array of tool calls in a single response. The secret sauce here is the tool call ID. Each request gets its own unique ID. So when the results come back after being run all at once, with something like Python's async io.gather, you can perfectly match each result to the right request. It just works. Okay, we've seen how powerful this is. Now we have to talk about the dark side. Because when an agent hallucinates, it's not just writing weird poetry. It can take real and sometimes disastrous actions. And this is the part that honestly most tutorials just skip right over. Failure mode number 1, wrong name. Super simple. The model calls get_invoice details when your function is actually called get_invoice. What happens? Your code throws an error. The whole thing just crashes. Number 2 is way scarier. Wrong tool. The model gets the right noun, invoice, but picks the wrong verb. It calls delete invoice instead of get invoice. The syntax is perfect, but the result? You just permanently destroyed customer data. Yikes. Okay, number 3, hallucinated arguments. This is where the model gets a little too creative. There was a real case where a scheduling agent was asked to book a meeting for one person, and it just invented a second person out of thin air and invited them. Boom. Confidential data leak. Number 4 is a classic. Missing a required parameter. The tool needs an invoice ID to work, but the model just forgets it. Now, if you have good schema validation, you'll catch this, but only if you've built that check yourself.
And finally, number 5, tool bypass. This is when the model just gets lazy. Instead of calling your get stock price tool to get the real data, it just confidently makes up a number. To your user, it looks totally legit, but it's 100% fake. So how do you actually defend against all this? You build a 3-layer defense. A big reason this happens is ambiguity. If you give a model 50 really similar tools, it's going to start guessing. So layer 1, schema validation. Before you run anything, you validate every single argument. Layer 2, a tool whitelist. The model can only call from a pre-approved list, period. And layer 3, observability. Log every call, every parameter, every result. That way you can spot failures when they happen.
These layers aren't just abstract ideas, right? They form a real architectural pattern. This is how we go from a little demo script to a rock-solid, production-ready system that can handle these problems gracefully. So here's what that production pipeline actually looks like. The LLM makes a request, but before anything runs, it goes through a validator, then a whitelist. Then the executor runs it, but with a timeout, so it can't hang forever. A circuit breaker is also a great idea. If a tool fails 3 times in a row, you block it. And of course, the logger tracks everything. A really robust system also practices context hygiene, only sending the model the few tools relevant to the current task. And it sets hard limits, like a max number of tool calls to stop any runaway loops.
And what's the payoff for all this? Well, just look at layer 1. If you use strict typed schemas with something like Pydantic instead of just raw JSON, you can cut parsing and validation errors from a crazy 40% all the way down to just 2%. That's a massive win for reliability from just one simple change.
Now, looking to the future, this whole mess of custom integrations is about to get a lot cleaner. There's an emerging standard called the Model Context Protocol, or MCP. The absolute best analogy for it is USB-C for tool calling, one universal protocol so any model can connect to any tool. Expect to see it adopted widely in 2025, and by 2026, it'll likely be the default. If you're building a tool layer today, you should absolutely be thinking about making it MCP compatible.
Okay, so let's boil this all down. What are the key takeaways? First, a tool call is just a JSON contract. The model proposes, you execute. Second, use parallel calls with something like asynchrono.gather. It's the biggest performance win you can get. And third, assume hallucinations will happen. Build your 3-layer defense. Validate, whitelist, and log everything.
And all of this leaves us with a really interesting, kind of provocative question. The best agents we're seeing today, they don't always have the biggest, smartest models. They have the most reliable tool layers. So that makes you wonder, what's the real brain of an AI agent? Is it the language model, or is it the rock-solid, dependable, and defensible engineering infrastructure that we build all around it?